Hello, dear friends. This is me, Asif Javed. I welcome one and all to my official YouTube channel, Maths Quest. Today, I will discuss a very important topic from number theory with you. Why I am discussing this topic with you has got many reasons, because the topic I am going to discuss with you has got many applications in modern algebra course. So today we will discuss about two important number theoretic function. One of them is sigma function and another one is tau function. So let me briefly tell you what is a sigma function and what is a tau function. In mathematics, we have got positive integers. And as far as the course of number theory is concerned, we are interested in certain aspects of a number. For example, we are interested in how many divisors a number has. Sometimes we are interested in sum of divisors of a number. So it is at this very point, these two functions will come to our rescue. Like if I talk about this tau function, this will give us a number theoretic way of calculating the number of divisors of any number. In fact, I must say any positive integer. Similarly, a sigma function gives you a number theoretic way of calculating the sum of divisors of a number. So let us first of all briefly define what is a tau function and what is a sigma function. So if I talk about tau function, if it comes to the definition of tau function, this tau function is a function from set of natural numbers to set of natural numbers. So this must be very clear to us that tau function has got its input from the set of natural numbers and it will take its value inside the set of natural number. How is it defined? This is a function from n to n and is defined as, this is defined as tau of n. This is equal to number of positive divisors of n. This can be written in this way: summation 1 d divides n. So this is the definition of tau of n. Let me give you an example. This will become crystal clear to one and all. Suppose I am interested in finding the number of divisors of 10. So I will write tau of 10. So this tau of 10, this is summation d divides 10, 1. Now you have to repeat 1 as many times as you have the divisors of 10. For example, if you will go on finding the divisors of 10, then you will have 1 divides 10. So corresponding to that, you will have 1 plus, again 2 will divide 10, then you have another 1. Then 5 divides 10, you have another 1. And then 10 also divides 10. So 1 plus 1 plus 1, that is equal to 4. So 1 will be divided 4 times, or to put it in a nutshell, I must say that 10 has got how many divisors? It has got exactly 4 divisors. Similarly, if you talk about divisors of suppose 30, divisors of 30, it will be defined in this way: d divides 30, 1. Now go on talking about the divisors of 30. 1 divides 30, so you will add 1. Then 2 divides 30, another 1. 3 divides 30, another 1. 5 divides 30. Then 10 divides 30. Then 15 will divide 30. And finally 30 will divide 30. So how many ones I have got? 1, 2, 3, 4, 5, 6, 7. Am I right? Let me first of all see. 1 divides, 2 divides, 3 divides, then 4, 5 divides, 6 also divides. I had missed 6. So this is also here. Then 7, 8, 9, nothing. Then 10 divides, then 15, and then 30. 1, 2, 3, 4, 5, 6, 7, 8. So how many ones I have got? 8. So number of divisors will be equal to 8. Now you must be thinking, since I have taken small numbers, so it isn't difficult to find the number of divisors for these small numbers. What if I take the numbers like 1,000, 10,000, 1 crore? So in that case, if we go on thinking in the same fashion, then we have to spend months together to find the number of divisors of those numbers. So this is where the number theory will come to our rescue. Number theory will give us a practical way of finding those, finding the number of divisors for those numbers also. So this was briefly the introduction of tau function. Now, along with tau function, we have another important number theoretic function, that is sigma function. What is the definition of sigma function? Again, it is a function from set of natural numbers to set of natural numbers. So this sigma function, this is again a function from set of natural numbers to set of natural numbers. This is defined by sigma of n. This is equal to sum of positive divisors of n. Simply you have to do what? D divides n, but now you will place d instead of 1. For example, you have to find sigma of 10, then you will write d divides 10 summation d. So you will keep on adding d's, you will keep on adding those d's which will divide 10. Previously what we were doing, we were adding 1 corresponding to the divisor of that number. So which will divide 10? 1 will divide 10. So we will write in place of d 1. Then 2 will divide 10. Then we will write 2. And 3 will not, 4 will not. Then 5 will divide 10. And then finally 10 will divide 10. So if we add all of them, it becomes 18. So sigma of 10 is equal to 18. Again, I will be, you must be thinking on the same lines that we had a very small number 10 and it was practically feasible for us to think about the divisors of 10. What if I take a big number, like if I think about a number like 30,000, or if I think about a number like 2,568, and like all these sort of numbers, because finding first of all divisors for those numbers and then adding it is altogether a I must say a tiresome exercise. So to reduce our exercise, number theory comes to our rescue. So this is why I am recording this lecture, just to let you know that number theory has blessed you with some important results, some number theoretic results. And if you make use of those results, you can find the answer for number of divisors and sum of divisors in not minutes, but in few seconds. So this is the next thing I am going to discuss with you. There are certain things which I will be skipping, because if I go into those things also, it will take some time. Like you must be knowing the concept of multiplicative function. If you don't know, I will briefly tell you what is a multiplicative function. So what is a multiplicative function? A function is said to be multiplicative if what happens? If f of mn is equal to f of m into f of n, and m and n must be relatively prime to each other. If you have any two integers and if you take the product of two integers and you apply the function on that, and then if you take the integers individually and you apply the functions on those integers, and if you then take the product of those two functions, then both the expressions are going to be same. So if f of m into n, this is same as f of m into f of n, provided m and n are relatively prime, then we say that f is multiplicative function. And as a matter of fact, tau and sigma functions are also multiplicative functions. So when I am saying that sigma and tau are multiplicative functions, I essentially mean that tau of mn, this is equal to tau of m into tau of n, provided GCD of m and n is equal to 1. Similarly, sigma of m into n, this is equal to sigma of m into sigma of n, provided GCD of m and n is equal to 1. This is okay. Now the proof of these results, it isn't too difficult. It makes use of unique factorization theorem. I will record the proof of multiplicativeness of these two functions in another lecture, but right now I actually want you guys to know about that important number theoretic result, which gives you some methodology of finding the sum of divisors of a number and number of divisors of a number. So let me take you straight to that theorem. What that theorem says, it says that if you have a number n equal to, what is the theorem? Listen to me carefully. I will be giving you the proof of this theorem also, because it isn't too difficult to prove. Suppose you have any number and you know that you can write any number as product of powers of distinct primes. So you can write any number. This is called fundamental theorem of arithmetic. So you can always write any number uniquely as a product of powers of distinct primes. So if you take any number n greater than 1, and if you have written that in terms of this product of power of primes, then this theorem says that if you take the tau of n, then tau of n will be equal to, simply you have to add 1 to the powers of all these primes. You add 1 to the alpha 1, you add 1 to alpha 2, so on, you add 1 to the alpha r, and then you take the product of all these quantities. So whatever you are getting, that will be the value of tau of n. Isn't it very interesting? So this means this is equal to pi, I goes from 1 to r, alpha I plus 1. This is just the compact notation. You can safely skip this notation. If this is a cumbersome notation for you guys, you can actually look at this. Simply what you have to do, you have to write n as the product of powers of primes, and then you have to look at the powers of primes only. And then what you do, you add 1 to each of these powers and then take the product. So whatever is the product, that is going to give you the answer of tau of n. So this is first thing we will be proving. Second thing is, what is sigma of n? So sigma of n is also equal to some quantity. So sigma of n will be equal to, this will be equal to, corresponding to this, we will be having p1 alpha 1 plus 1 minus 1 upon p1 minus 1. Corresponding to this, we will be having p2 alpha 2 plus 1 minus 1 upon p2 minus 1 into, and so on. This will be PR alpha r plus 1 minus 1 upon PR minus 1. Now this is the expression for finitely many prime distinct powers of primes. Suppose if you have only one prime, then your expression will stop here only. If you have two power of primes, then the expression will stop here. So simply depending upon the number of distinct primes that you have in the factorization of any number, so your expression will get adjusted accordingly. Suppose if you have 4 primes, power of primes in your expression, then you will be having the product of 4 such quantities. So this is how you find sigma of n. Now you must be thinking, what about the proof? A proof, it isn't that difficult. You just need to recall the definition of sigma n and tau n, and the proof will surrender itself in front of us. So let us do the proof of this immediately, so that we are confident enough that whatever we are using, we also know the proof of that. So let us first of all find the proof for tau of n. Now what is this tau of n? This tau of n is equal to p1 alpha 1, p2 alpha 2, and so on, pr alpha r. Now, since this tau is multiplicative and all of these are relatively primes, and whatever is true for two things, that thing can be extended for n number of quantities. So if two numbers were relatively prime, and if in that case tau was multiplicative function, here you can see that all of them are relatively prime. So we can make use of the multiplicativeness of tau. So this will be equal to tau p1 alpha 1 into tau p2 alpha 2 into tau pr alpha r. Now stop for a moment and let us first of all look at tau of p1 alpha 1, because once we catch hold of tau of p1 alpha 1, that will give us rhythm for calculating tau of p2 alpha 2 and so on up to tau pr alpha r. So what is this tau of p1 alpha 1? This is nothing but this is number of divisors. This is by definition number of divisors of p1 alpha 1. Technically speaking, this is nothing but this is d divides p1 alpha 1 1. So you will repeat 1 as many times as are the divisors of p1 alpha 1. So how many divisors of p1 alpha 1 we have? Look carefully. It will have, this is p1 alpha 1, it will have divisors 1, p1, p1 2, p1 3 and so on up to p1 alpha 1. All of them will divide p1 alpha 1. Are you sure? This divides, and after that nothing will divide this. So how many divisors p1 alpha 1 has? From 1 to alpha 1 there are alpha 1 divisors and 1 is also, so it will have alpha 1 plus 1 divisors. So we have seen that it has alpha 1 plus 1 divisors. So tau of p1 alpha 1 being the number of divisors of p1 alpha 1, this will have answer as alpha 1 plus 1. On the basis of similarity grounds, we can write this as alpha 2 plus 1 and so on. This is alpha r plus 1. And this is the proof. This is what I told you. Now coming to the sigma function. Coming to the sigma function. By sigma function, we mean the sum of divisors. Now this is sigma function. This is p1 alpha 1, p2 alpha 2, and so on, pr alpha r. Now this will be equal to sigma p1 alpha 1, sigma p2 alpha 2, and so on, sigma pr alpha r. Now firstly we will find for p1 alpha 1 and that will give us the rhythm for finding for others. Simply you have to find sum of divisors of p1 alpha 1. But you know what are the divisors of p1 alpha 1? Take their sum. This is 1 plus p1 square and so on plus p1 alpha 1. Now if you look at this expression carefully, this is a finite GP. And you know what is the sum for finite GP? This is a into r raised to power n minus 1 upon r minus 1. Where r is the common ratio and n is the number of terms in that finite GP. If you look at this expression, you will find that it has alpha 1 plus 1 terms. That means n will be equal to alpha 1 plus 1. And if you look at the common ratio, then the common ratio is p1. And if you look at the first term is 1. So all of what you will get out of this is 1 into what is r? This is p1 raised to power alpha 1 plus 1 minus 1 upon r minus 1, that is p1 minus 1. So what you have got? You have got p1 raised to power alpha 1 plus 1 minus 1 upon p1 minus 1. So this is what we got for this. p1 raised to power alpha 1 plus 1 minus 1 upon p1 minus 1. So taking inspiration from this, we can safely write p2 raised to power alpha 2 plus 1 minus 1 upon p2 minus 1. And then we can extend this up to this. So this will be pr alpha r plus 1 minus 1 upon pr minus 1. So this is your sigma function. Now let me take some examples. This was the proof. Proof wasn't that difficult, that I told you in the very beginning. Now let me tell you how we can apply this. Suppose I take a very big number. Let me take 2022. And I want to find the number of divisors and sum of divisors of 2022. So first of all, you have to do is you just find the factorization of that number. So this will be, then you divide it by 3. 3 3s are 9. This is again 3 3s are 9. 3 7s are 21. 7 3. Now this will not be, I think you have to stop here. Can you divide this by any other number? This is going to be the prime number. Let us try. 9 is not going to divide this. 11, then 12, 13. 13 is it going to divide? 13 2, 26, 26 and 6. No. 14, no. 15, nothing. 16, 17. 17 ones are 17. Then you have 17 and 16, 167. 7, no, it will not. 19, 19's 1, 19 ones are 19. Then we have how much? This is 20, then 13, for 147. So let me see if 147 can be divided by 19. 19 into 8. Let me write 6. 9s are 54, 5, 6, 5, 11. 19, 7, 8, 8. 9s are 2, 7, 15. 19, 9. Now it will not. 1, 17. So it will not, even by 19, it will not be divided. So we can say that this 337, this is prime number. Now this tau of 2020, let me take a simple number because this is all about factorization. If you can get rid of the factorization properly, suppose I take 10,000. So you can write this as 10 raised to power 4. Fine. So you can write it as 2 into 5 raised to power 4. So you can write it as 2 power 4, 5 power 4. Now you just have to look at the powers. You add 1 to the powers and then multiply them. So this is 5 into 5, that is 25. That means number of divisors for this will be 25. Now again, if you look at the sigma of this will be this. Now what you have to do, you add 1 to the power, that is 2 raised to power 5 minus 1 upon 2 minus 1. Then you add 1 to the power 5 raised to power 5 minus 1 upon 5 minus 1. So what you get, 2 raised to power 5 is 32 minus 1 is 31 by 1 into, this is 125 minus 1. This is 124 by 4. Then if you divide this, this is 4 3s are 12, 4 1s are 4. So this is 31 into 31. What is 31 into 31? This is 3. This is 3. This is 9. This is 1. This is 6. This is 9. This is 961. That means if you add up the divisors of this number, then you are going to get the sum as 961. Similarly, you can take other numbers and find out the number of divisors and sum of divisors for the number. So this is all I have for you guys regarding this sigma and tau function. Before I end today's lecture, I must tell you one thing, that these two number theoretic functions have got immense or tremendous applications as far as your contemporary abstract algebra is concerned. Like if you will study their Zn, then you can find the number of subgroups of Zn. This is simply tau of n. You can find number of generators of this Un as phi of n. You can find dihedral group, the number of subgroups of dihedral group as sigma n plus tau n. So these number theoretic function will come to your rescue. They will give you some idea about finding the number of parameters or number of key elements that are present in abstract algebra. So they are very helpful regarding that. This phi function, in fact, this was the Euler's phi function. I will make use of this. I will tell you about this function in some other lecture. Right now, I have told you about tau function and sigma function, and these two functions are very important number theoretic function when it comes to their application. So thank you so much and have a nice day.